Hi, this is Rod Badicke from Streamsim Technologies, and this talk is about applying material balance to reservoir pattern surveillance models. For mature floods, estimating the remaining oil in place distribution is a cornerstone of prudent reservoir management. This ROIP distribution can be estimated from reservoir simulation or material balance calculations. However, reservoir simulation requires expert knowledge and additional efforts such as history matching before reliable ROIPs are computed. The advantage of material balance is that history is used directly, it is easier to apply and understand, but it does lack the resolution of flow simulation. Traditionally, material balance in reservoir pattern surveillance workflows has been limited to fixed well patterns. Yet we know that patterns are dynamic, as explained in the highlighted link. So a better approach is to account for this dynamic nature. Furthermore, accurate material balance calculations should also account for the geology, the variability in initial fluid saturations and pressures, the changing well rates, presence of aquifers, and PVT properties. In real fields, we use a numerical method to trace the streamlines that shares many details with traditional reservoir simulation. We require a 3D grid, geological and PVT properties, the historical well rates and their paths. Then we solve the pressure equation, apply Darcy's law to determine the velocity field, and then trace streamlines numerically such that they follow this velocity field. For surveillance models, we apply material balance to each well pair pore volume, and we do this as follows. We know the volume of water injected into each well pair because of the well rate allocation factor, or WAF. The volumes of oil, water, and gas produced from each well pair are also known because of the allocation factor. And the streamline paths give us the volume of oil, water, and gas within the pore volume. Then, from material balance, if we know the in-place volumes, plus how much was injected, less how much was produced, then we can compute how much is remaining, as shown by the equation in the middle of the screen. Finally, these volumes are then converted to average saturations that remain in the well pair pore volume. Note, unlike reservoir flow simulation where the solution to the transport equations results in a waterfront moving from the injector to the producer, here we are solving a zero-dimensional equation, meaning that the saturation distribution within the pore volume must always be assumed to be uniform. This material balance calculation is repeated for each unique well pair pore volume that exists in the current time step. Once all the pore volume saturations are updated on the underlying grid, we advance to the next time step. To account for the fact that the patterns are dynamic, the historical well rates are updated to the next time step. Here, new wells may come online or shut in or switch from producer to injector. Then the velocity field is recomputed from the new pressure solve, which then updates the new streamlines, the allocation factors, and the dynamic patterns. The material balance process for each new well pair is repeated, and the overall time stepping process repeats until we reach present day. To give an example of this material balance method when applied to dynamic patterns, we use injection and production history from 1963 to 2004 for a mature flood. Assuming that the initial oil distribution and geology is uniform as shown in the upper left image. You can see that by 1974, the upper image on the right, that the remaining oil in place as shown by the green and yellow colors has been reduced where there is injection and production. Also note that the remaining oil volume shapes follow the well pair bundle pore volumes and how those have changed from 1963 to 1974. The material balance process is repeated each year, and by 1995, the lower left image, remaining oil is reduced as the green areas grow. By 2004, high remaining oil is only on the edges of the model. Also shown are the cumulative bubbles of water injected in light blue and water produced dark blue. Thus, consistent with the areas of water injection and oil production, remaining oil in place is reduced in those areas on the grid. If we repeat this material balance calculation on the exact same field used in the previous slide, but with a different 3D distribution of initial oil in place as shown on the left. Notice how the remaining oil in place for this field is now more centrally located compared with the previous slide. Thus, as a caution, the remaining oil in place distribution computed from material balance at the end of history is a strong function of the initial oil in place distribution, as expected. As a reminder, this method is fully 3D. And if we include compressible PVT properties, then the 3D pressure distribution can also be computed. For this reservoir, shown on the upper left is the initial pressure distribution, and on the upper right is the final pressure distribution. Areas in red are high pressures where there is active injection, while blue areas are lower pressures. Similarly, on the lower left image is the initial oil saturation distribution. Note that there is a gas cap in the upper right and a water leg in the lower left of this image. Then on the lower right image is the final distribution of oil saturation after applying dynamic material balance. While the remaining oil saturation distribution lacks the detail of flow simulation, we still see areas of high and low saturations. As mentioned at the start of this presentation, the goal is to compute the remaining oil in place distribution. Thus, for the model in the previous slide, multiplying the remaining oil saturation in the top left image by the pore volume in the bottom left image, and then collapsing all the layers into a 2D stacked model and viewing from the top, as in the figure on the right, we can show where the remaining oil is regionally located in this field. Red areas have high remaining oil, while blue areas have low remaining oil. In summary, we have shown how we apply material balance to dynamic well patterns for reservoir surveillance models. Specifically, we use streamline region metrics to define the well pair pore volumes on which the material balance calculations are applied. The advantages of this approach are that only the major flow units are required in the geo model, we account for the dynamic patterns, there's no history matching, and these models are relatively easy to build, run, and explain. The disadvantage of this approach is that we cannot model transport effects, such as those due to gravity, capillarity, or resolving fronts. The saturation profiles that are determined from this method are coarser in resolution compared to traditional reservoir simulation. And this method is not meant for segregated reservoirs that have commingled production and injection, unless special considerations are made. We call our method Streamline Region-Based Material Balance, and it is part of our 3DSL simulator. I'm Rod Badeke, and thank you for listening. If you have any questions, please visit us at streamsim.com or email us at support@streamsim.com. Thank you.